Picture this. The universe is a vast crime scene, and we're the detectives piecing together clues billions of years old. The case: how lifeless stardust transformed into the building blocks of life itself. Today we're cracking open one of science's greatest mysteries, the origin of organic molecules in space, with 30 groundbreaking theories that'll rewrite how you see our cosmic beginnings. Some of these ideas will sound like science fiction, others like pure magic, but each one represents serious scientific detective work, from primordial soups simmering on early Earth to alien delivery systems aboard meteorites, from deep-sea chemistry labs to interstellar molecular factories. We're about to uncover how the universe might have cooked up its first ingredients for life. What makes this investigation so thrilling? Every new space mission and lab discovery brings us closer to solving the ultimate whodunit: how atoms became us. And here's the kicker: somewhere in these 30 theories, we might just find the answer. Ready to join the cosmic cold case squad? Let's examine the evidence. Now let's step into the laboratory of history, where one of the most famous experiments in science gave us our first real clue about life's origins. Back in 1953, two young chemists, Stanley Miller and Harold Urey, decided to recreate early Earth's atmosphere in a glass maze of flasks and tubes. Their goal: to see if life's basic ingredients could form under conditions that mimicked our planet's violent infancy. They filled their setup with what they believed were Earth's primitive gases: methane, ammonia, hydrogen, and water vapor, then subjected it to continuous electrical sparks to simulate lightning. What happened next was nothing short of astonishing. Within days, the once clear liquid turned a murky brown, and when they analyzed it, they found something groundbreaking: amino acids, the very building blocks of proteins essential for life. This experiment gave birth to the Primordial Soup Hypothesis, the idea that Earth's early oceans, charged with energy from lightning or volcanic activity, could have brewed life's first molecules in a nutrient-rich broth. It was a revelation. For the first time, scientists had evidence that complex organic compounds could arise from simple chemistry, no divine spark required. But like any great theory, this one isn't without its skeptics. Some argue that Earth's early atmosphere might not have been as rich in methane and ammonia as Miller and Urey assumed, potentially making their experiment less accurate. Others point out that while amino acids are crucial, they're just one piece of the puzzle. Forming proteins and genetic material is a far more complicated leap. Yet here's why this theory still matters. Even with its limitations, the Miller-Urey experiment proved that organic molecules can form naturally under the right conditions. Modern research has expanded on their work, showing that different combinations of gases or energy sources like UV light or shockwaves from meteor impacts can yield similar results. Plus, scientists have found amino acids in meteorites, suggesting that even if Earth's exact conditions were different, the universe itself seems primed for organic chemistry. So while the primordial soup might not be the whole story, it was the first real taste of how life's ingredients could emerge from cosmic chaos. It set the stage for decades of exploration, and as we'll see next, newer discoveries are adding unexpected flavors to this simmering pot of possibilities. Stay tuned. Now let's fast forward to the 21st century, where cutting-edge science is giving the primordial soup hypothesis a major makeover. While Miller and Urey's experiment laid the foundation, modern researchers have uncovered twists that make this classic theory even more intriguing. One of the biggest updates: Earth's early atmosphere might not have been the methane-rich playground Miller and Urey imagined. Instead, scientists now suspect it was dominated by carbon dioxide and nitrogen, with volcanic eruptions spewing out hydrogen sulfide and other sulfur-based gases. So what happens when you recreate those conditions? Experiments show that volcanic lightning striking these mixtures can still produce amino acids, just in different combinations. It turns out the soup doesn't need a single recipe to work. Then there's the discovery of interstellar formaldehyde. This simple molecule is everywhere in space, detected in molecular clouds and even comets. Here's the kicker: when formaldehyde dissolves in water, it can react to form sugars like ribose, a key ingredient in RNA. Imagine comets delivering this interstellar ingredient to Earth's early oceans, enriching the primordial soup with extraterrestrial sugar. Suddenly, the idea of life's building blocks brewing in a cosmic kitchen doesn't seem so far-fetched. But the updates don't stop there. Hydrothermal vents, those underwater geysers teeming with chemistry, might have acted as natural reactors. Lab experiments show that when you mix vent-like minerals with simple carbon compounds, you get more than just amino acids. You get chains of molecules that resemble early proteins. And if those vents were near volcanic islands, tidal cycles could have concentrated these molecules in shallow pools, creating hotspots for chemistry to climb toward complexity. The real takeaway: the primordial soup wasn't a one-pot wonder. It was a dynamic, ever-changing mixture stirred by volcanoes, seasoned by space dust, and simmered in countless environments across the young Earth. What began as a groundbreaking experiment in the 1950s has blossomed into a vibrant field where chemistry, geology, and astronomy all stir the pot together. So while the soup metaphor still holds, we now know it wasn't just sitting on a cosmic stove. It was a bubbling, evolving cauldron with ingredients from the stars themselves. And that's just the beginning. Next, we'll dive into the deep sea vents where some scientists believe life might have taken its first fiery breath. Now let's plunge into the depths of the ocean, where another compelling theory for life's origins comes into focus. Far from the sunlit surface, hydrothermal vents on the seafloor create environments so extreme and yet so chemically rich that they've been called the blacksmiths of early life. Picture underwater chimneys spewing superheated water loaded with minerals into the icy darkness. These aren't just geological oddities, they're potential cradles for the first organic molecules. Take the Lost City hydrothermal field, discovered in the year 2000 in the Atlantic Ocean. Unlike the more famous black smoker vents, which gush acidic, metal-laden fluids, Lost City's vents are alkaline, powered by a process called serpentinization. Here, seawater reacts with mantle rocks to produce hydrogen gas and heat, while also creating microscopic pores and channels in the vent structures. These tiny nooks are where the magic happens. Experiments show that the mineral-laden fluids can drive simple carbon compounds like carbon dioxide to assemble into more complex molecules, including acetic acid and even amino acids like glycine. It's like a molecular factory, with the vents providing both the raw materials and the energy to stitch them together. What makes these environments so special? 3 key ingredients. First, the heat gradient. Scalding water meeting near freezing ocean creates a natural flow of energy that could have powered early chemical reactions. Second, the mineral surfaces, particularly iron-sulfur clusters, act as catalysts, helping molecules bond in ways that would be unlikely in open water. And third, the constant churn of fluids means fresh ingredients are always cycling through, preventing chemical dead ends. But the most striking evidence comes from modern vents. Researchers have detected amino acids like alanine and aspartic acid in the fluids swirling around these systems, molecules that are fundamental to life as we know it. Even more intriguing, some vents host porous rocks with microscopic compartments that mimic the structure of cell membranes. These spaces could have concentrated and protected early organic molecules, giving them a stable environment to interact and evolve. The vent hypothesis doesn't just explain how organic molecules might form, it also tackles the energy problem. Life needs a constant power source, and vents provide it in spades, with chemical disequilibria that could have driven the first metabolic reactions. It's a theory that ties together geology, chemistry, and biology in a way few others can. painting a vivid picture of life's possible beginnings in the fiery, mineral-rich depths of a young Earth's oceans. Yet, as we'll soon see, not all vents are created equal. The debate between alkaline and acidic vents opens another fascinating chapter in this story. But here's where things get even more interesting. Not all hydrothermal vents operate under the same conditions, and this split between alkaline and acidic vents sparks one of the most heated debates in origins of life research. On one side, you've got the classic black smokers towering chimneys billowing dark, acidic plumes at temperatures hot enough to melt lead. These vents are rich in iron and sulfur, creating a harsh environment where certain key chemical reactions might have thrived. The iron-sulfur minerals lining these vents, like pyrite, could have acted as primitive catalysts, helping simple molecules combine into more complex ones. In fact, some lab experiments show that iron-sulfur clusters can facilitate the formation of amino acids and even small peptides, the building blocks of proteins. It's a compelling case, especially since these metals are still central to many of life's core enzymes today. On the other side, we have the gentler, but no less intriguing alkaline vents like Lost City. Instead of scorching acidity, these systems produce warm, mineral-rich fluids through serpentinization, a process where water reacts with certain types of rock to generate hydrogen gas and a highly alkaline environment. Unlike black smokers, these conditions might have been better at protecting delicate organic molecules from breaking apart, while still providing the energy needed for assembly. The microscopic pores in these vent structures could have acted like tiny test tubes, concentrating reactants and shielding them from the destructive forces of the open ocean. Now, which model holds more weight? Alkaline vents have a few standout advantages. Their chemistry naturally produces hydrogen, which could have powered some of life's earliest metabolic processes. They also create gradients differences in pH and temperature that mimic the energy-generating mechanisms found in modern cells. Some researchers argue that these gradients might have been the original battery for life, long before more complex energy-harvesting systems evolved. Yet black smokers shouldn't be dismissed. Their high iron-sulfur content ties directly into theories about early metabolism, particularly the iron-sulfur world hypothesis, which suggests that life's first energy-capturing reactions revolved around these metals. Plus, the sheer abundance of such vents on the early Earth means they would have been widespread and active, offering countless opportunities for organic synthesis. So where does that leave us? It's possible both types of vents played a role, acidic ones forging key molecular ingredients, while alkaline vents provided stable environments where those ingredients could combine and evolve. Or perhaps one type dominated in certain regions while the other took the lead elsewhere. What's clear is that hydrothermal vents, in all their diversity, offer some of the most plausible settings for life's molecular beginnings. And as research continues, we might find that the real story is even more nuanced than we imagine. Next, we'll venture beyond Earth altogether to explore how the cosmos itself could have seeded the building blocks of life. Now, let's take a cosmic leap beyond Earth's oceans and consider a radically different idea. What if life's ingredients didn't originate here at all? This brings us to Panspermia, the theory that organic molecules, or even primitive life, might have hitched a ride to our planet aboard comets, meteorites, or interstellar dust. Imagine the universe as a vast delivery network, scattering the building blocks of life across star systems. One of the most compelling pieces of evidence for this theory comes from the Murchison meteorite, a space rock that landed in Australia in 1969. When scientists analyzed its contents, they were stunned. Inside, they found over 70 different amino acids, the same molecules that form proteins in all living things. Even more fascinating, some of these amino acids aren't commonly found on Earth, suggesting they formed in space. This wasn't a fluke. similar organic compounds have been detected in other meteorites like the Tagish Lake and Orgale specimens, painting a picture of a cosmos rich with prebiotic chemistry. But how could these delicate molecules survive the violent journey to Earth? Here's where things get tricky. When a meteorite enters our atmosphere, it's subjected to extreme heat, thousands of degrees, enough to vaporize most organic material. However, studies show that larger meteorites, especially those with carbon-rich compositions, can act like cosmic heat shields. Their outer layers may burn up, but the interior can remain relatively cool, preserving fragile molecules. Even comets, which are essentially icy dirt balls, could have delivered organics by scattering them in their tails or embedding them in protective icy matrices that slowly released upon impact. There's another twist. Some researchers propose that radiation in space might have actually helped forge these molecules, not just transport them. In the frigid void between stars, icy dust grains can accumulate simple chemicals like water, ammonia, and methanol. When hit by cosmic rays or ultraviolet light, these ices undergo reactions that create complex organics, a process replicated in labs by zapping ice mixtures with radiation. This means the raw materials for life might have been crafted in the depths of interstellar clouds long before reaching a planet. Of course, Panspermia isn't without its skeptics. One major hurdle is the question of timing. Even if space rocks carried organics, could they have delivered enough to kickstart life before Earth's own environments took over? And while amino acids are essential, they're not life itself. How would they have transitioned into self-replicating systems here? Still, the idea gains traction from discoveries like the asteroid Ryugu, where samples returned by Japan's Hayabusa 2 mission contained intact amino acids, proving these molecules can endure space travel. Whether Panspermia was a primary driver or just one of many contributors, it reshapes how we view life's origins. It suggests Earth wasn't an isolated laboratory but part of an interconnected cosmic network, where the seeds of biology might be older and more widespread than we ever imagined. Next, we'll delve into an even more controversial spin on this idea, the notion that these cosmic deliveries weren't entirely accidental. Now, let's venture into a twist on Panspermia that pushes the boundaries of scientific speculation. What if those cosmic deliveries weren't random but intentional? This is the essence of directed Panspermia, a provocative idea suggesting that advanced extraterrestrial civilizations might have deliberately seeded life's building blocks across the cosmos. One of the most notable figures behind this concept was Nobel Prize-winning biologist Francis Crick, who co-discovered the structure of DNA. In the 1970s, Crick and chemist Leslie Orgel floated the idea that microbial life could have been purposefully sent to Earth by intelligent beings, perhaps as a way to jumpstart biology on a young planet. At first glance, this might sound like science fiction, but Crick's hypothesis was rooted in a genuine scientific puzzle. He argued that the sudden appearance of life's molecular machinery, like DNA's intricate coding system, seemed too complex to have emerged unaided in Earth's early history. Directed Panspermia, he suggested, could explain this leap. Imagine an ancient alien civilization packaging hardy microbes or organic precursors into asteroid-like vessels and launching them toward habitable worlds. It's a cosmic version of sowing seeds, with Earth as one potential garden. Critics, however, point out glaring issues. For starters, there's zero direct evidence of such a mission. While meteorites carry organics, none bear traces of artificial engineering or signatures that would distinguish them from natural processes. Plus, the distances between stars make interstellar travel daunting even for advanced civilizations. Even at light speed, sending probes to neighboring systems would take centuries or millennia, raising questions about why any species would undertake such a project. And if they did, why not leave clearer markers of their involvement? Another sticking point is Occam's razor, the principle that the simplest explanation is usually the correct one. Natural panspermia, where organic molecules spread via asteroids or comets without guidance, already accounts for the presence of space-borne amino acids and nucleobases without invoking intelligent designers. Experiments show these molecules form readily in space clouds or planetary conditions, making directed seeding seem unnecessary. Even Crick himself later conceded that natural processes might suffice, though he maintained that directed panspermia couldn't be ruled out entirely. Yet the idea persists in fringe circles, often conflated with claims about ancient astronauts or UFOs. What makes it enduring despite skepticism is its tantalizing blend of mystery and possibility. It taps into a deeper question. If life's origins are extraordinarily rare, could deliberate seeding be a way for intelligence to ensure its survival or propagation? Some modern theorists even play with variants like lithopanspermia, where microbes hitchhike on rocks ejected by planetary impacts, spreading naturally but effectively. For now, mainstream science leans heavily toward naturalistic explanations. Missions like NASA OSIRIS-REx, which returned samples from asteroid Bennu, focus on decoding how organic chemistry unfolds in space without assuming external guidance. The discovery of ribose, a sugar critical for RNA in meteorites, further strengthens the case that prebiotic chemistry is a universal process, not requiring alien intervention. Whether you find directed panspermia intriguing or outlandish, it serves as a reminder of how wide open the question of life's origins remains. It challenges us to ask not just how life began, but whether we're alone in crafting the answer. Next, we'll shift from speculative delivery systems to the cold, dark nurseries of interstellar space, where molecules may have formed long before planets even existed. Turning our gaze from the fiery drama of directed panspermia to the quiet vastness of interstellar space, we find a cosmic nursery where chemistry unfolds on a scale almost beyond comprehension. Here, in the freezing darkness between stars, sprawling molecular clouds, vast regions of gas and dust act as silent laboratories for some of the universe's most intricate organic chemistry. These clouds, often light years across, are far from empty. They're teeming with molecules that could hold the keys to life's origins, and radio telescopes are our window into this hidden world. When scientists point these telescopes toward nebulae like Sagittarius B2, a giant molecular cloud near the center of our galaxy, they don't just see simple gases. They detect a surprising menagerie of complex organics, including glycolaldehyde, a sugar molecule that's a direct precursor to ribose, the backbone of RNA. How do these fragile molecules survive in space? The answer lies in the icy dust grains drifting through these clouds. Picture tiny motes of silicate or carbon, each coated in layers of frozen water, carbon monoxide, and methane. These icy shields protect delicate molecules from the harsh radiation that would otherwise break them apart, while also providing a surface where chemistry can happen. Laboratory experiments simulating these conditions reveal something remarkable. When simple ices like water and ammonia are exposed to the kinds of cosmic rays and ultraviolet light found in space, they react to form more complex compounds, including amino acids and even the nucleobases found in DNA. The process is slow, think millions of years, but in the deep time of the cosmos, that's barely a blink. What's more, these icy grains don't just shelter molecules, they help build them. Quantum tunneling, a bizarre effect where particles jump through energy barriers they shouldn't be able to cross, allows reactions to occur even at temperatures close to absolute zero. The implications are staggering. If complex organics can form in the depths of space, then the raw materials for life might have been present in the solar system's birth cloud long before Earth even existed. When the young sun and planets coalesced from this cloud, those molecules could have been baked into asteroids, comets, and eventually delivered to our planet's surface. This isn't just speculation. Missions like Rosetta, which studied comet 67P, found glycine, the simplest amino acid, in its icy nucleus. What makes this theory so compelling is its universality. Unlike planetary scenarios tied to Earth's unique geology or chemistry, interstellar molecular clouds are everywhere. If they're factories for life's ingredients, then the universe might be seeded with organics on a scale we're only beginning to grasp. Next time you look up at the night sky, remember, the darkness between stars isn't empty. It's simmering with the promise of chemistry that could one day spark life anew. Now let's take a step deeper into these cosmic chemistry labs, specifically the frigid, pitch-black realms of dark molecular clouds. Here, where temperatures hover just a few degrees above absolute zero, conventional chemistry would seem impossible. Yet somehow, against all odds, the building blocks of life emerge. How? The secret lies in a phenomenon as strange as it is essential: quantum tunneling. Picture this: in a lab on Earth, scientists recreate the icy depths of space by chilling a vacuum chamber to nearly -270 degrees Celsius. They coat a surface with layers of water, ammonia, and methanol, common ices found on interstellar dust grains, then bombard them with ultraviolet light or cosmic rays. What happens next defies intuition. Instead of remaining inert, these simple molecules begin transforming into complex organics, including nucleobases like adenine and guanine, key components of DNA and RNA. Here's where quantum tunneling changes the game. At such extreme cold, molecules lack the thermal energy to overcome the energy barriers required for most chemical reactions. But in the quantum realm, particles don't always follow classical rules. Electrons and protons can tunnel through these barriers as if they were ghostly apparitions, enabling reactions that would otherwise stall. This isn't science fiction. It's been measured in labs and even observed in space. For example, the formation of water in dark clouds relies on tunneling, with oxygen and hydrogen atoms merging despite the freezing environment. One groundbreaking experiment at the University of Hawaii demonstrated this vividly. Researchers simulated interstellar ice chemistry and found that glyphosate, a molecule once thought too complex to form in space, could emerge through tunneling-aided reactions. Even more striking, these processes aren't rare. The same team calculated that tunneling could accelerate certain reactions in space by a factor of 1,000,000 compared to traditional chemistry. But tunneling isn't the only force at work. The structure of the ice itself plays a crucial role. These ices aren't uniform solids. They're porous, with microscopic tunnels and cages that trap molecules, holding them in close proximity long enough for quantum effects to take over. It's like a cosmic assembly line where ingredients are prearranged for maximum efficiency. The implications ripple far beyond our solar system. If these mechanisms operate universally, then the raw ingredients for life, nucleobases, sugars, amino acids, could be synthesized in the darkest, coldest corners of every galaxy, waiting to be incorporated into newborn planets. Missions like the James Webb Space Telescope are now hunting for these molecular fingerprints in distant clouds, and every discovery adds weight to the idea that life's blueprint might be written into the fabric of the cosmos itself. So next time you hear about the chill of outer space, remember, it's not a lifeless void. It's a quantum-enabled workshop, silently crafting the very molecules that could one day spark life anew. Now, let's shift our focus from the icy depths of space to the ancient, mineral-rich landscapes of early Earth. Picture this: warm, shallow pools fringed by volcanic rocks, their surfaces coated with fine, layered clays. These unassuming minerals might hold one of the most overlooked keys to life's origins. This brings us to a groundbreaking idea proposed by chemist Graham Cairns-Smith, the clay mineral catalysis theory. Imagine clays not just as passive dirt, but as dynamic scaffolds that actively helped assemble the first organic molecules. Here's how it works. Clay minerals like montmorillonite or kaolinite have layered structures with charged surfaces. These surfaces attract and concentrate simple molecules such as nucleotides, the building blocks of RNA. but they don't just gather them, they organize them. The repeating patterns in clay act like molecular templates, aligning nucleotides in ways that make it easier for them to link into chains. Lab experiments have shown this in action. In one study, researchers mixed nucleotides with montmorillonite clay, and under the right conditions, the clay catalyzed the formation of RNA-like strands up to 50 units long. That might not sound like much, but for prebiotic chemistry, it's a huge leap. Without clays, these reactions would require extreme conditions or take far longer. But with clays, they happen relatively easily in settings that could have been common on early Earth. Why does this matter? Because RNA is central to the RNA world hypothesis, the idea that life began with self-replicating RNA molecules. But RNA is notoriously finicky. It's hard to make under plausible early Earth conditions. Clays could solve that problem. They provide a Goldilocks environment, not too harsh, not too mild, but just right for organizing and stabilizing these delicate molecules. And clays don't stop at RNA. They can also concentrate amino acids, helping them form peptides, the precursors to proteins. Some clays even have catalytic properties that speed up these reactions. For example, certain clay minerals can facilitate the formation of peptide bonds in water, something that's otherwise extremely difficult without modern enzymes. The implications are profound. If clays played this role, then life might not have needed exotic environments or rare events to get started. Instead, it could have emerged in the quiet, mineral-rich shallows of volcanic lakes or coastal sediments where clays were abundant. This theory doesn't just fill a gap in the story of life's origins, it turns ordinary dirt into a cosmic architect. So, next time you see clay, remember, what looks like simple mud might have been the unsung hero that helped assemble the very first molecules of life. And with new research exploring how clays interact with other prebiotic chemistries, this humble mineral might yet reveal even more secrets about our deepest origins. Now, let's take this idea even further and explore how Cairns-Smith's clay theory beautifully bridges into one of the most compelling frameworks for life's origins, the RNA world hypothesis. Imagine a scenario where clay minerals didn't just passively gather molecules, but actively set the stage for the first genetic material to emerge. The RNA world hypothesis suggests that before DNA and proteins, life ran on RNA, a molecule that can both store genetic information and catalyze chemical reactions, much like an all-in-one tool. But here's the puzzle: RNA is complex. Building it from scratch under early Earth conditions seems unlikely without some kind of molecular helper. That's where clays come in. Recent experiments show that clay surfaces don't just organize nucleotides, they actively promote the formation of RNA-like polymers. In one groundbreaking study, scientists observed that montmorillonite clay could stitch together activated nucleotides into chains up to 50 units long, all without the need for modern enzymes. What makes this so remarkable is the simplicity. The clay's layered structure provides a charged surface that lines up nucleotides in just the right orientation, making it easier for them to chemically bond. Think of it like a molecular assembly line where the clay acts as the factory floor, keeping everything in place while the building blocks snap together. This process isn't just a lab curiosity, it's a plausible pathway for how RNA might have formed in nature without requiring perfect conditions or rare events. But the story doesn't end there. Clays also address another major hurdle for the RNA world: stability. RNA is fragile, especially in water where it tends to break apart. Yet, clay minerals can protect these nascent strands, shielding them from degradation while still allowing them to interact with other molecules. Some clays even have pockets or grooves that could have served as tiny reaction chambers, concentrating reactants and boosting the chances of successful polymerization. This hybrid model, where clays and RNA co-evolved, offers an elegant solution to multiple problems at once. Clays provide the scaffolding and catalysis, while RNA brings the versatility needed for replication and function. It's not hard to imagine how these two systems could have worked together, with clays jump-starting the process and RNA eventually taking over as the dominant player in early biochemistry. And the evidence keeps growing. Researchers have found that certain clays can also help RNA strands replicate by holding templates in place while new strands form. This hints at a potential transition from clay-driven chemistry to a true RNA world, where self-replicating molecules could eventually escape their mineral origins and kickstart the evolution of life as we know it. So, while the RNA world hypothesis once seemed like a bold but uncertain idea, the clay connection grounds it in tangible chemistry. It's a reminder that life's origins might not hinge on a single dramatic event, but on the quiet, persistent partnership between molecules and minerals, a partnership that turned simple dirt into the foundation of biology. Now, let's switch gears and explore a theory that literally sparks curiosity: electric spark synthesis. While lightning often steals the spotlight in origin of life discussions, lesser-known electrical phenomena like corona discharges might have played an equally shocking role in creating life's building blocks. Picture Earth's early atmosphere thick with volcanic fumes and swirling gases. Amidst this chaos, not just lightning but also smaller, more frequent electric discharges. Think crackling sparks around volcanic plumes or static charges in dust clouds could have been busy forging organic molecules. Laboratory experiments back this up. When scientists simulate these conditions by zapping mixtures of methane, ammonia, and water vapor with corona discharges, something remarkable happens. Nucleobases, the informational core of DNA and RNA, start to form. One landmark study recreated these tiny sparks in a sealed flask, mimicking the faint but persistent electrical activity around ancient volcanoes. The result: adenine and guanine, two of life's crucial nucleobases, emerged in detectable amounts. Unlike the brute force of lightning, these gentler discharges might have offered a more sustainable environment for delicate molecules to accumulate over time. But why does this matter? Because it broadens the playground for life's origins. Volcanoes were rampant on early Earth, and their plumes loaded with charged particles and turbulent gases would have been prime real estate for corona discharges. These sparks could have turned volcanic rifts into natural laboratories, churning out nucleobases without requiring the perfect storm of a lightning strike. Here's another twist: these discharges might have worked hand in hand with other theories. Imagine electric sparks generating nucleobases in volcanic clouds, which then rained down into tidal pools or hydrothermal vents where clays or minerals could further organize them. It's a team effort where no single process had to do all the heavy lifting, and the implications stretch beyond Earth. Similar electric phenomena occur in the hydrocarbon-rich atmospheres of places like Titan, Saturn's moon. If spark synthesis works here, why not there? It's a tantalizing hint that the universe might have multiple ways to jumpstart the chemistry of life. No lightning required, just a little cosmic static. So, while lightning gets the dramatic headlines, it's the quieter, persistent crackle of corona discharges that might have been the unsung hero in building life's first molecules. Next time you hear a spark, remember, it could be the sound of chemistry writing its own origin story. Now let's step into the light literally, with photochemical synthesis, where the universe uses sunlight as its ultimate chemistry lab. While electric sparks and hydrothermal vents grab attention, there's something quietly brilliant happening when ultraviolet light strikes icy surfaces in space. Take Saturn's moon Titan, a frozen world with methane lakes and a hazy orange sky. Here, UV radiation transforms simple molecules like methane and nitrogen into tholins, those mysterious reddish-brown organic compounds that could hold clues to life's ingredients. Picture Titan's surface, where sunlight breaks apart methane molecules in the upper atmosphere. These fragments recombine into increasingly complex chains, forming tholins that rain down onto icy plains. Lab experiments on Earth mimic this process by blasting icy mixtures with UV light, and the results are striking. Within hours, simple gases morph into organic goo packed with amino acids and nucleobases, molecules essential for life as we know it. But here's why this matters for Earth's story. 4 billion years ago, our planet might have had Titan-like conditions in places. Shallow pools filled with hydrocarbons under a young sun pouring out intense UV radiation could have been prime spots for photochemical soup making. Unlike the deep-sea vents or volcanic sparks we've discussed, this process doesn't need heat or electricity, just sunlight and the right chemicals. One compelling piece of evidence comes from Earth's own extreme environments. In places like Iceland's hot springs, scientists find UV-driven reactions creating organic molecules even today. And if you think about it, early Earth's atmosphere lacked today's protective ozone layer, meaning UV light hit the surface with far greater intensity. Every sunlit puddle brimming with methane or ethane could have been a tiny factory for prebiotic molecules. What's fascinating is how photochemical synthesis complements other theories. Imagine tholins forming in the atmosphere, then washing into tidal pools where clays or minerals helped organize them. Or picture these organics drifting into hydrothermal vents where heat and minerals further refine them. It's another reminder that life's origins might not hinge on a single eureka moment, but on countless processes working in concert, and the implications stretch beyond our solar system. Exoplanets with hydrocarbon-rich atmospheres could be undergoing similar chemistry right now. If UV light can cook up complex organics on Titan, why not on worlds orbiting red dwarfs or in distant nebulae? The universe might be teeming with photochemical laboratories, quietly assembling the pieces of life under the glow of alien suns. So while we often focus on Earth's fiery or watery origins, let's not forget the power of light. From Titan's haze to Earth's primordial pools, photochemistry offers an elegant, energy-efficient path to life's first molecules. No lightning or vents required, just the gentle, relentless touch of sunlight. Now, let's take a detour from the usual suspects like sunlight and deep-sea vents and explore a far lesser-known but equally intriguing idea, the radioactive beach hypothesis. Imagine this: 4 billion years ago, stretches of coastline shimmering not just with water, but with traces of uranium and thorium embedded in the sand. These seemingly hostile environments might have been unexpected cradles for life's earliest molecules. At the heart of this theory is monazite, a mineral found in certain sands that contains small amounts of radioactive elements. When these elements decay, they release energy in the form of gamma radiation. Now, you might think radiation is purely destructive, but here's the twist: it can also drive chemical reactions. In lab experiments, scientists have recreated primordial tidal zones using monazite sand and simple chemical solutions. Over time, the radiation from these minerals breaks apart water molecules, generating reactive hydrogen and oxygen radicals. These radicals, in turn, can stitch together simple carbon-based molecules into more complex organics, like amino acids or even sugars. What makes this scenario compelling is its specificity. Unlike broad atmospheric processes, radioactive beaches offer tiny, concentrated pockets of energy perfect for localized chemistry. Picture a tide pool where waves wash over monazite-rich sand, creating a cycle of wetting and drying. Each time the water recedes, newly formed organics could concentrate on mineral surfaces, protected from degradation while radiation continues supplying energy for further reactions. Critics argue that radiation's destructive effects might outweigh its benefits, but here's where the balance matters. Low to moderate radiation levels, like those near monazite grains, could provide just enough energy to kickstart chemistry without obliterating delicate molecules. Plus, minerals in the sand might act as shields, absorbing harmful radiation while still allowing beneficial reactions to occur nearby. This idea also ties into broader themes. Earth's early crust was likely richer in radioactive isotopes than today, meaning such beaches could have been more common. And let's not forget the role of tides themselves. Rising and falling waters would have constantly mixed and replenished chemical ingredients, creating a dynamic laboratory. So why hasn't this theory gained more traction? For one, it's harder to study than, say, hydrothermal vents or lightning-filled skies. But recent experiments are breathing new life into the idea. One study showed that radioactive minerals could catalyze the formation of peptide short chains of amino acids under conditions mimicking early Earth. If these findings hold, radioactive beaches might deserve a spot alongside classic theories in the origin of life puzzle. This isn't just about Earth either. Exoplanets with radioactive shorelines could be undergoing similar chemistry right now. It's a reminder that life's building blocks might have assembled in the unlikeliest of places, powered not by sunlight or geothermal heat, but by the quiet, persistent energy of atoms falling apart. So next time you walk along a beach, consider this: what if the gentle waves once carried not just sand, but the seeds of life itself? Now, let's shift our gaze from Earth's beaches to the chaos of space, where another explosive theory takes center stage: meteorite impact synthesis. Picture this: the early solar system was a shooting gallery, with asteroids and comets slamming into young planets at unimaginable speeds. But instead of just destruction, these violent collisions might have been cosmic blacksmiths, forging the very molecules life needed to begin. At the heart of this idea is a simple but powerful concept. When a meteorite hits, it doesn't just leave a crater. The shock waves from these impacts generate extreme pressures and temperatures, turning the impact zone into a temporary laboratory for organic chemistry. Carbon-rich asteroids packed with simple compounds like water, ammonia, and methane could have been the perfect raw materials. When these asteroids struck Earth or even other bodies in space, the energy of the impact might have rearranged those simple ingredients into something far more complex. Lab experiments back this up. Scientists have recreated these violent conditions using high-powered guns or lasers to simulate meteorite strikes. In one study, a team fired projectiles at mixtures resembling carbonaceous chondrites, a type of asteroid rich in organic material. The result, amino acids, the building blocks of proteins, formed almost instantly under the extreme pressures. These pressures, reaching hundreds of thousands of times Earth's atmosphere, can force molecules together in ways that gentle chemistry simply can't match. What makes this theory stand out is its universality. Unlike Earth-bound processes that depend on specific environments like vents or tides, impact synthesis could have happened anywhere, on asteroids, moons, or even the surface of Mars. Some researchers even suggest that the organic molecules found in meteorites today might not just be relics of space chemistry, but could have been forged during the impacts that blasted them off their parent bodies. But here's where it gets even more intriguing. These impacts wouldn't have just created organics, they could have delivered them. When a carbon-rich asteroid hits a planet, the heat and pressure might cook up new molecules on the spot, but the debris from that impact could also scatter organic material far and wide. Imagine a meteorite striking Earth's early oceans, not only creating amino acids in the impact zone, but also splashing them into surrounding water where they could accumulate and interact. Of course, there are challenges. Critics point out that the same extreme conditions that create organic molecules can also destroy them. Too much heat and everything breaks down. But here's the balance. Some impacts would have been just right, intense enough to drive reactions, but not so violent that they obliterated the products. Plus, minerals in the asteroids or the target surface could have acted as buffers, absorbing excess energy and protecting delicate molecules. This theory also ties into one of the biggest mysteries in astrobiology: how life's ingredients spread so widely. If impacts can both create and deliver organics, they might explain why we find amino acids in meteorites and why similar molecules pop up in simulations of distant planetary systems. It's a reminder that the universe doesn't just build life's pieces in quiet corners, it might hammer them together in the chaos of collisions. So next time you see a shooting star, remember, it's not just a streak of light. It could be a glimpse of the violent, creative forces that might have put the first pieces of life in motion. And who knows, somewhere out there, another impact could be forging the next chapter in this cosmic story. Now, let's dive into one of the most controversial yet fascinating ideas on our list: cold fusion at ocean floors. While the term cold fusion might sound like something out of science fiction, some researchers believe it could have played a role in creating the building blocks of life. This theory takes us to the dark, mineral-rich depths of Earth's ancient oceans, where unconventional chemistry might have been at work. The idea hinges on a process called low-energy nuclear reactions, or LENR. Unlike the extreme temperatures and pressures of traditional nuclear fusion, cold fusion suggests that nuclear reactions could occur at much lower energies, even in environments like underwater mineral deposits. Proponents point to nickel-rich seabeds where certain minerals like nickel and hydrogen might interact in ways that release energy that could have driven the formation of organic molecules. Lab experiments have fueled this debate. In some studies, researchers observed anomalous heat production when nickel and hydrogen were combined under specific conditions. While mainstream science remains skeptical, cold fusion has been a contentious topic since its controversial debut in the late 20th century. These anomalies keep the conversation alive. Could similar reactions have occurred naturally in Earth's early oceans, providing the energy needed to assemble life's first ingredients? One compelling piece of the puzzle comes from hydrothermal vent systems, particularly those rich in nickel and other transition metals. These metals can act as catalysts, helping simple molecules like carbon monoxide and hydrogen combine into more complex organics. If cold fusion-like reactions were happening alongside these catalytic processes, they might have provided an extra push, accelerating chemical reactions that would otherwise take much longer. But let's balance the scales. Critics argue that cold fusion lacks reproducible, peer-reviewed evidence that meets rigorous scientific standards. Many of the reported anomalies could stem from measurement errors or unconventional chemical reactions rather than actual nuclear processes. Even if some form of low-energy nuclear interaction exists, the energy output might be too minimal to significantly impact prebiotic chemistry. Yet the theory refuses to fade entirely. Some researchers propose a middle ground. Perhaps what's happening isn't conventional cold fusion, but a poorly understood form of metal-assisted chemistry that mimics some of its effects. Nickel, for example, is known to facilitate unusual hydrogen interactions, which could still play a role in organic synthesis without invoking full-blown nuclear reactions. What makes this idea worth discussing is its sheer audacity. If even a fraction of the claims hold weight, it would rewrite our understanding of how energy flows in natural systems. Imagine a scenario where Earth's ocean floors weren't just passive sites for chemistry but active reactors, quietly generating the energy needed to kickstart life. So, where does that leave us? Cold fusion at ocean floors remains a fringe theory, but fringe ideas often push science forward. Whether it's ultimately validated or debunked, it challenges us to think outside the box, and in the search for life's origins, that's never a bad thing. The ocean floor, with its hidden mineral wealth and untapped mysteries, might still have surprises left to reveal. Now, shifting gears from the depths of the ocean to the steamy edges of geothermal pools, let's explore another compelling theory: how the natural ebb and flow of wet and dry cycles could have been a catalyst for life's earliest molecules. Picture this: bubbling hot springs on ancient Earth, where water constantly evaporates and refills, creating a rhythm that might have been perfect for stitching simple molecules into something more complex. The magic here lies in polymerization, the process of linking small molecules like amino acids into longer chains such as peptides. For life to emerge, these chains needed to form reliably, and geothermal pools offer a unique setting where this could happen. Researchers have found that when amino acids are dissolved in water and then exposed to cycles of drying and rewetting, mimicking what would happen at the edge of a hot spring, they naturally bond together into peptides. It's like nature's way of pressing the fast-forward button on chemistry. One groundbreaking experiment demonstrated this beautifully. Scientists recreated early Earth conditions by placing amino acids in a solution and subjecting them to repeated wet-dry cycles. Each time the water evaporated, the amino acids concentrated, bringing them closer together. When water returned, the molecules reacted more easily, forming peptide bonds. Over time, these cycles produced chains of amino acids, essentially the building blocks of proteins. What's remarkable is that this process doesn't require any fancy catalysts or extreme conditions, just the simple, predictable rhythm of a geothermal pool. But why are these cycles so effective? For one, drying removes water molecules, which can interfere with peptide bond formation. Without water in the way, amino acids are free to link up. Then when water returns, it helps shuffle the molecules around, setting the stage for the next round of bonding. It's a bit like kneading dough. Each fold and press strengthens the structure. Geothermal pools add another layer to this story. Unlike stagnant ponds, these environments are dynamic, with heat and minerals constantly stirring the pot. The heat speeds up chemical reactions, while minerals like silica or clay can act as scaffolds, helping amino acids align in ways that make bonding easier. Some studies even suggest that the mineral-rich edges of these pools could have selectively favored certain amino acid combinations, nudging chemistry toward the complexity needed for life. Of course, this isn't a perfect theory. Critics point out that while peptides are crucial, they're still a long way from full-fledged proteins or self-replicating molecules. Plus, not all amino acids polymerize equally well under these conditions. Some might get left behind. But the beauty of this idea is its simplicity. It doesn't rely on rare events or exotic environments. Instead, it taps into a process that would have been happening all over the early Earth, wherever hot springs bubbled and evaporated. What makes this theory stand out is how elegantly it bridges chemistry and geology. It's a reminder that life's origins might not have required a single dramatic event, but rather the steady, patient work of natural cycles, ones that are still at play today in places like Yellowstone's hot springs or Iceland's geothermal fields. So next time you see steam rising from a pool, imagine the possibilities. That same gentle cycle of wet and dry could have been the quiet architect of life's first molecules. Now let's turn our attention to the fiery landscapes of ancient Earth, where volcanic activity might have played a starring role in the story of life's first molecules. Enter the sulfur world hypothesis, a theory that suggests sulfur-rich volcanic gases could have been the unsung heroes of early metabolism. Picture the early Earth, dotted with active volcanoes spewing not just lava, but also clouds of sulfur dioxide and hydrogen sulfide. These gases, often dismissed as just toxic fumes, might have been the key to unlocking energy-rich compounds essential for life. At the heart of this idea are thioesters, molecules that could have acted as primitive versions of ATP, the energy currency of modern cells. Thioesters form when sulfur atoms bond with carbon, creating a high-energy link that can power chemical reactions. So how does this work? In modern cells, ATP stores energy in its phosphate bonds, releasing it when needed. But before ATP existed, thioesters could have served a similar role. Sulfur-rich volcanic environments would have been perfect for their formation. When hydrogen sulfide reacts with simple organic molecules, like those delivered by comets or formed in hydrothermal vents, thioesters can emerge. These compounds are remarkably versatile. They can donate energy to drive other reactions or even help build more complex molecules, acting as a kind of molecular battery for early chemistry. One of the most compelling pieces of evidence for this theory comes from lab experiments. Scientists have recreated volcanic conditions, mixing sulfur gases with simple organics under moderate heat. The result, thioesters form readily, along with other sulfur-containing molecules that could have been early metabolic players. What's fascinating is that some of these sulfur compounds are still used by certain modern microbes, hinting at a deep evolutionary connection. But why sulfur? For one, it's incredibly reactive, making it great for jump-starting chemistry. It also forms stable bonds with carbon, creating durable energy carriers. Plus, sulfur was abundant on the early Earth, especially around volcanic regions. Unlike phosphorus, another key element in modern metabolism, sulfur doesn't get easily locked away in minerals, meaning it would have been freely available for reactions. Of course, the sulfur world hypothesis isn't without its challenges. Critics argue that while thioesters are useful, they're not as efficient as ATP in storing energy. And without enzymes to regulate their use, it's unclear how early systems could have managed these molecules effectively. But proponents counter that life didn't start with perfection. It started with what worked well enough. Thioesters might have been the stepping stone that paved the way for more advanced energy systems. What makes this theory so intriguing is how it ties geology to biochemistry. Volcanic activity wasn't just shaping the planet's surface, it might have been shaping the very chemistry of life. And while we often think of volcanoes as destructive, this perspective reminds us that they could have been creative forces too. So next time you catch a whiff of sulfur, whether from a hot spring or a struck match, take a moment to appreciate its role in the grand story of life. It's a humble element, but without it, the energy to power life's earliest steps might never have existed. And that brings us to our next theory, where we'll explore how another simple molecule, iron, could have teamed up with sulfur to build the foundations of life. Now, imagine a scenario where the spark of life didn't just rely on sulfur alone, but also found a powerful partner in iron. This brings us to the iron-sulfur world theory, a fascinating idea proposed by scientist Günther Wechtersheuser that shifts the spotlight to the dynamic chemistry happening on the surface of iron sulfide minerals, particularly pyrite, also known as fool's gold. Picture this, deep beneath the ocean, where hydrothermal vents spew mineral-rich fluids into the water, iron and sulfur come together to form tiny, crystalline surfaces. These surfaces aren't just passive bystanders, they're active participants in the dance of early chemistry. Wechtersheuser's theory suggests that pyrite's unique structure could have acted as a primitive scaffold, attracting simple carbon-based molecules and encouraging them to link up into more complex chains. Here's how it might have worked. Pyrite forms when iron reacts with hydrogen sulfide, releasing tiny particles with a positively charged surface. This positive charge is crucial because it can attract negatively charged molecules like carbon dioxide or simple organic compounds, holding them in place just long enough for reactions to occur. On these mineral surfaces, carbon dioxide could have been converted into more complex molecules like acetic acid, a key building block for life. One of the most compelling aspects of this theory is how it tackles the energy problem. In modern cells, energy is stored in molecules like ATP, but early chemistry needed a simpler solution. Pyrite formation actually releases energy, and Wechtersheuser proposed that this energy could have been harnessed to drive the synthesis of organic molecules. It's like the mineral itself was a tiny power plant, fueling the reactions that built life's first ingredients. Lab experiments have added weight to this idea. Scientists have recreated vent-like conditions, mixing iron and sulfur with carbon monoxide and water. Under these settings, they've observed the formation of acetic acid and even more complex molecules, all clinging to the pyrite surfaces. What's remarkable is that these reactions don't require enzymes or other biological machinery, just the right mix of minerals and conditions. But the iron-sulfur world theory goes beyond just making simple molecules. It also offers a potential pathway to metabolism. Pyrite surfaces could have hosted a primitive version of the citric acid cycle, a fundamental metabolic process in modern cells. Instead of enzymes guiding the reactions, the mineral's surface geometry might have directed the chemistry, creating a rudimentary but functional metabolic network. Of course, no theory is perfect, and this one has its skeptics. Some argue that while pyrite can facilitate certain reactions, it's not clear how these processes could have transitioned into the sophisticated biochemistry we see today. Others point out that the conditions required might have been too specific to be widespread, but supporters counter that hydrothermal vents provide a stable, long-term environment where such chemistry could have played out over millennia, gradually refining itself into something more complex. What makes this theory so compelling is its elegance. It ties together geology, chemistry, and biology in a way that feels almost inevitable. Iron and sulfur were abundant on the early Earth, and their interactions could have set the stage for life without requiring any exotic ingredients. It's a reminder that sometimes the most ordinary materials can give rise to the extraordinary. As we move forward, keep in mind that life's origins might not have relied on a single eureka, a moment, but on a series of small, incremental steps, each building on the last. And with that, let's turn our attention to another piece of the puzzle: how simple sugars, essential for life structure, might have formed in the chaotic chemistry of the early Earth. Now, let's shift gears and explore a reaction so elegant it almost feels like nature showing off. The Foremost reaction, where simple formaldehyde molecules team up to create the sugars life desperately needed. Picture this: a warm, alkaline pool on the early Earth, rich with formaldehyde, a compound we've detected in space and know could have been delivered by comets or formed in volcanic plumes. In this setting, something remarkable happens. Formaldehyde molecules, which are just one carbon atom with two hydrogen atoms and an oxygen, begin linking together like train cars, eventually forming sugars like ribose, the backbone of RNA. Here's why this reaction is such a big deal. Ribose isn't just any sugar, it's the R in RNA, the molecule many scientists believe was life's first genetic material. Without ribose, the RNA world hypothesis hits a snag. The Foremost reaction offers a plausible way this critical sugar could have emerged naturally without any biological help. The magic happens under alkaline conditions, like those near certain hydrothermal vents or in evaporating tidal pools. Formaldehyde molecules react with each other in a series of steps, first forming tiny 2 and 3 carbon sugars, then eventually branching into larger ones like ribose. It's a bit like a molecular domino effect. One reaction triggers the next, building complexity along the way. But there's a catch: the Foremost reaction isn't picky. It produces a mix of sugars, not just ribose, and many of them are useless or even disruptive to life's chemistry. So how did nature select the right sugar? One intriguing answer involves minerals like borate. Recent experiments show that borate, which could have been present in early Earth's hot springs, binds specifically to ribose, stabilizing it amid the chaotic soup of other sugars. It's like a molecular bouncer, letting ribose stay while escorting the others out. Lab studies have recreated this process, demonstrating that under the right conditions, alkaline pH, trace metals, and borate, the Foremost reaction can indeed produce ribose in meaningful amounts. Even more compelling, these conditions mirror environments we think existed on the early Earth, like serpentinizing vents where alkaline fluids rich in minerals mingled with carbon compounds. Yet, skeptics point out challenges. The Foremost reaction can be finicky, too much heat or the wrong pH, and it devolves into a tarry mess. Plus, ribose is notoriously unstable over geologic timescales, leading some to wonder if it could have accumulated enough to kickstart life. But here's a twist: while ribose might not stick around forever, its fleeting existence could have been enough. If other molecules, like nucleobases, were nearby, they might have quickly teamed up with ribose to form more stable RNA-like chains, sidestepping the decay problem altogether. What makes this theory so captivating is its blend of simplicity and specificity. Formaldehyde is a cosmically common molecule, and alkaline environments were likely widespread on the early Earth. Together, they could have set the stage for carbohydrates to emerge, filling a critical gap in life's origin story. As we piece together these chemical puzzles, remember, each theory is a thread in a grand tapestry, showing how ordinary ingredients under the right circumstances could weave the extraordinary story of life. And with that, let's turn to another contender, the role of phosphorus, an element so vital to life's blueprint that its cosmic scarcity has sparked some of the most creative theories yet. Now, let's tackle one of life's most puzzling ingredients, phosphorus. Without it, life as we know it simply wouldn't exist. Phosphorus is the backbone of DNA, the energy currency of cells, and a key player in cell membrane. But here's the catch: phosphorus is notoriously scarce in forms that life can use, creating what scientists call the phosphorus problem. So how did early Earth get enough of this critical element to kickstart biology? The answer might lie in meteorites. Picture this: billions of years ago, space rocks packed with a rare mineral called schreibersite, a phosphorus-rich compound, bombarded our planet. When these meteorites crashed into Earth's watery surface, something extraordinary happened. Schreibersite, which contains phosphorus bound to iron and nickel, reacted with water, releasing phosphorus in a form that could easily link up with organic molecules. Lab experiments have shown this process can produce phosphorylated compounds, the very building blocks of life's energy systems and genetic material. But why is this such a big deal? On Earth's surface, phosphorus is usually locked up in rocks like apatite, which barely dissolves in water, making it nearly inaccessible for chemical reactions. Schreibersite, on the other hand, is like a phosphorus vault that bursts open on contact with water. This could have created concentrated pockets of reactive phosphorus in places like hydrothermal vents or tidal pools, where other organic molecules were already gathering. One fascinating experiment recreated early Earth conditions by mixing schreibersite with water and simple organic compounds. The result: phosphorus quickly integrated into molecules like phosphate esters, which are crucial for RNA and energy-carrying molecules like ATP. Even more compelling, this process works best in slightly acidic water, similar to the conditions around volcanic vents or in carbon dioxide-rich early oceans. Yet, skeptics raise valid questions. While schreibersite delivers phosphorus in a usable form, could there have been enough meteorites to supply the quantities needed for life's origin? Recent estimates suggest yes. During Earth's early bombardment phase, enough schreibersite-laden meteorites may have hit the planet to seed multiple environments with reactive phosphorus. Plus, some scientists propose that lightning strikes on volcanic ash rich in phosphorus could have generated additional sources, adding another layer to the puzzle. What makes this theory so compelling is its cosmic connection. Schreibersite isn't just an Earth-bound curiosity. We've found it in meteorites like the famous Canyon Diablo, which formed Arizona's meteor crater. This means the phosphorus problem might have a universal solution. Wherever planets are bombarded by the right kind of space rocks, the ingredients for life's energy and genetics could follow. As we piece together these clues, one thing becomes clear. Life's origin wasn't just about organic molecules, it was about the right minerals delivering the right elements at the right time. And with that, let's turn to another twist in the story, the surprising role of fatty acids and how they might have built life's first protective bubbles. Now, let's shift gears to a theory that flips the script on how life might have organized itself from the very beginning. Imagine a world where the first step toward life wasn't genetic material or energy-carrying molecules, but something far simpler: tiny, protective bubbles. This is the essence of the lipid membrane first hypothesis, which suggests that fatty acids, the building blocks of cell membranes, could have been life's first architects. Fatty acids are remarkable molecules. In water, they spontaneously assemble into tiny spheres called vesicles, with their water-loving heads facing outward and their water-repelling tails tucked inside. These lipid bubbles aren't just passive containers, they're dynamic structures that can grow, divide, and even concentrate molecules inside them. Experiments have shown that under conditions mimicking early Earth's geothermal pools or tidal flats, fatty acids readily form vesicles, creating microscopic compartments that could have housed the earliest chemical reactions of life. Why does this matter? Think of these vesicles as nature's first test tubes. By trapping organic molecules inside, they would have protected fragile reactions from harsh environments, like ultraviolet radiation or sudden temperature changes, while also concentrating reactants to speed up chemical processes. Some studies even demonstrate that lipid membranes can help organize molecules like RNA, potentially bridging the gap between simple chemistry and the complex machinery of life. One striking piece of evidence comes from hydrothermal vents. Certain fatty acids, like those with 10 to 20 carbon atoms, are stable in the warm, mineral-rich waters found near these systems. When researchers simulate vent conditions, these fatty acids not only form vesicles but also exhibit a surprising behavior. They can grow by absorbing nearby lipids and then split into daughter vesicles when agitated by waves or currents. This mimics a primitive form of reproduction, hinting at how early protocells might have multiplied without any genetic instructions. But the story gets even more intriguing. Lipid membranes aren't just physical barriers, they're selective gates. Some vesicles allow small molecules to pass through while trapping larger ones, creating an environment where beneficial reactions could thrive. For example, experiments show that vesicles made of certain fatty acids can accumulate nucleotides, the building blocks of RNA, effectively setting the stage for genetic material to emerge inside these protective bubbles. Critics, of course, raise questions. Could fatty acids have been abundant enough on early Earth? The answer might lie in meteorites again. The Murchison meteorite, famous for its organic richness, contains fatty acid precursors, suggesting space could have delivered these key ingredients. Alternatively, volcanic terrains or atmospheric reactions might have produced them locally. What makes this theory so compelling is its simplicity. Before complex genetics or energy systems, life might have needed just one thing: a way to separate inside from outside. Lipid vesicles provide that a humble yet profound starting point. And as we'll see next, this idea isn't just about containment. It's about how these bubbles might have set the stage for life's next big leap. Now, let's venture into a cosmic twist on the origins of life's building blocks. One that doesn't rely on Earth's surface or even deep sea vents, but on the invisible rain of high-energy particles from space. Picture this: Earth's early atmosphere, thick with methane and nitrogen, is constantly bombarded by cosmic rays speeding protons and atomic nuclei from distant supernova or other violent cosmic events. When these particles slam into atmospheric molecules, they trigger cascades of chemical reactions that could have showered the planet with organic compounds. This is the essence of the cosmic ray-driven chemistry theory, and it's not as far-fetched as it might sound. Take methane, for example. Under the assault of cosmic rays, methane molecules break apart, forming reactive fragments like methyl radicals. These fragments can then recombine with other atmospheric components like ammonia or carbon monoxide to form more complex organics, including amino acids and nucleobases. Researchers at CERN Cloud Experiment have recreated these conditions in their lab, exposing artificial atmospheres to particle beams that mimic cosmic rays. The results: a cocktail of organic molecules, some of which are direct precursors to life's essential ingredients. What's fascinating here is the sheer scale of this process. Cosmic rays aren't rare, they're a constant drizzle across the universe, and early Earth, lacking a strong magnetic field, would have been even more exposed. Calculations suggest that over millions of years, this cosmic rain could have deposited significant amounts of organics across the planet, especially in high-altitude regions where the atmosphere is thinner and cosmic rays penetrate more deeply. But the story doesn't end with simple molecules. Cosmic rays also ionize atmospheric gases, creating charged particles that act as catalysts for further reactions. In the cloud experiments, these ionized clusters were shown to dramatically accelerate the formation of aerosols, tiny particles that can clump together and fall to the surface, delivering their organic cargo to ponds or oceans below. This could have provided a steady supply of prebiotic material, even in environments otherwise too harsh for organic synthesis. Critics might argue that cosmic rays are too destructive to build complexity, given their reputation for breaking DNA in modern organisms. But early Earth's atmosphere was likely far denser, acting as a buffer that would have absorbed much of the damaging energy while still allowing beneficial chemistry to occur. Plus, the mix of cosmic rays and other energy sources like UV light or lightning could have created a balanced system where destruction and construction worked in tandem. The implications stretch beyond Earth. If cosmic rays can forge organics here, they might do the same on exoplanets with similar atmospheres, broadening the range of worlds where life could arise. It's a reminder that the universe doesn't just passively host life. It might actively help build it one high-energy particle at a time. And as we'll see next, this isn't the only way space could have played midwife to life's first molecules. Now, let's turn our gaze to an atmosphere thick with organic smog, a world where sunlight filters through dense hydrocarbon hazes, conditions that might sound alien but could have been a reality on early Earth. This theory suggests our planet once resembled Saturn's moon Titan, with skies filled with methane and nitrogen that cooked up a rich organic brew under ultraviolet light. Imagine a young Earth, its atmosphere shimmering with an orange-brown haze. Unlike today's clear skies, this haze would have been packed with Tholen's complex organic molecules formed when simple hydrocarbons like methane are zapped by UV radiation. These tholins aren't just random gunk. In lab experiments mimicking Titan's atmosphere, scientists have watched them assemble into amino acids and nucleobases, the very building blocks of life. Here's where it gets intriguing. While Titan's tholins stay frozen in its frigid atmosphere, early Earth's warmer climate could have let these organic particles dissolve into raindrops or settle into ponds. Picture a shallow pool, its surface shielded from harsh UV by the very haze that created its contents. Over time, these protected pockets might have concentrated enough organic material to kickstart chemical evolution. But how do we know this isn't just speculative? Studies of Titan provide a natural laboratory. The Cassini spacecraft detected tholins in its atmosphere, and while Titan's surface is too cold for liquid water, Earth's temperate zones wouldn't have that limitation. Researchers have simulated early Earth conditions by irradiating methane-nitrogen mixtures, producing tholin-like compounds that, when soaked in water, spontaneously form membranous structures, protocells that could have been life's first containers. Critics might question whether such hazes could persist long enough to matter. Yet geologic evidence hints at periods when Earth's atmosphere was rich in methane, possibly due to volcanic outgassing or microbial activity. Even short-lived haze episodes could have delivered significant organics. Plus, the UV shield effect is a game-changer. By blocking harmful radiation while allowing beneficial chemistry, these hazes might have created safe zones where delicate molecules could accumulate without being destroyed. The implications ripple outward. If hydrocarbon hazes helped life emerge here, exoplanets with similar atmospheres might follow the same recipe. It's a reminder that what seems like a gloomy, smog-filled sky could actually be a cosmic kitchen, quietly simmering the ingredients for life. And as we'll soon see, this isn't the only environment where hidden energy sources might have worked their magic. Now, let's shift our focus to a place where Earth's hidden energies might have sparked life's earliest chemistry, deep beneath the surface where water meets radioactive heat. Picture this, a steamy geyser, not just any geyser, but one fed by uranium-rich rocks, its waters laced with natural radiation. This is the nuclear geyser model, a fascinating hybrid theory that combines the power of geology and atomic energy to explain how life's building blocks could have gotten their start. Here's how it works. In certain regions, like the ancient rock formations of Gabon or parts of Canada, uranium deposits sit nestled in the crust. When groundwater seeps through these rocks, it gets heated by radioactive decay, creating geothermal systems with a twist. Unlike regular hot springs, these nuclear geysers would have been bathed in ionizing radiation, a surprising ally in prebiotic chemistry. Radiation might sound destructive, but at the right levels, it can drive chemical reactions that ordinary heat can't. For instance, experiments show that gamma rays can split water molecules, producing reactive hydrogen and oxygen species that help forge complex organics like formaldehyde and hydrogen cyanide, key ingredients for life's molecular toolkit. But the real magic happens in the geyser's cycling waters. As the water evaporates and condenses, it creates wet-dry cycles, a crucial factor for concentrating molecules and encouraging them to link up into longer chains. Imagine a shallow pool near the geyser's vent, where amino acids or nucleotides energized by radiation repeatedly dry out and rehydrate. Each cycle nudges them closer to forming peptides or RNA-like strands. Add in the mineral-rich environment with clays or metal sulfides acting as catalysts, and you've got a recipe for molecular complexity. What makes this theory stand out? It solves two big puzzles at once. First, the radiation provides a steady, localized energy source, unlike lightning or UV light, which are sporadic. Second, the geyser's structure offers natural compartments. Bubbles or mineral pores could have trapped and protected early molecules, creating microscopic labs where chemistry could experiment undisturbed. Support comes from modern analogs. Scientists have found microbes thriving in uranium mines, proof that life can not only endure but exploit radiation. Of course, skeptics ask whether these conditions were widespread enough to matter. But early Earth had far more radioactive isotopes like uranium-235, which decays faster than today's dominant uranium-238. That means more heat, more radiation, and possibly countless nuclear geysers dotting the landscape. Combine that with evidence from Mars, where similar uranium-rich regions exist, and suddenly this niche idea gains cosmic relevance. The nuclear geyser model reminds us that life's origins might not have been a single eureka, a moment but a slow simmer in Earth's hidden kitchens, places where water, rock, and radiation conspired to turn simple molecules into something extraordinary. And as we'll see next, even colder, quieter corners of the early universe might have held their own surprises. Now, here's a curious twist in the story of life's beginnings, one that scientists are still unraveling. Why does life on Earth overwhelmingly favor left-handed amino acids? It's like going to a party where everyone inexplicably uses only their left hand to shake yours. In chemistry, molecules can come in mirror image versions called chiral forms, and while nature produces both left and right-handed amino acids, life as we know it uses almost exclusively the left-handed ones. So what tipped the scales? One compelling idea points to the stars literally. When starlight travels through space, it can become polarized, meaning its waves vibrate in a particular direction. Some researchers suggest that polarized light from neutron stars or other cosmic sources could have selectively broken down right-handed amino acids more than their left-handed counterparts. Experiments back this up. When circularly polarized light, which spirals in one direction, shines on a mix of amino acids, it can create a slight excess of one hand over the other. Over millions of years, even a tiny imbalance could have snowballed into the overwhelming preference we see today. But the cosmos isn't the only suspect. Down on Earth, certain minerals might have played matchmaker. Take calcite crystals, for example. Their surfaces have tiny, asymmetrical grooves that can preferentially bind one type of amino acid over the other. Imagine these crystals as microscopic assembly lines, sorting and concentrating left-handed molecules while ignoring their right-handed twins. In lab tests, calcite and similar minerals have indeed shown this bias, hinting that geology could have nudged life's chemistry toward a left-handed world. Then there's the cold, quiet reaches of space. In icy molecular clouds where temperatures hover near absolute zero, quantum effects can influence chirality. Some theories propose that interactions between electrons and magnetic fields in these frigid environments could have favored one form over the other. When these ices later bombarded young planets via comets or meteorites, they might have delivered a pre-made bias toward left-handed molecules, a cosmic head start for life's building blocks. Of course, skeptics wonder if this chirality puzzle is even solvable. After all, life's preference might just be a frozen accident, a random fluke that stuck. But the fact that similar amino acid biases have been found in meteorites suggests the answer lies beyond Earth. Whether it was starlight, minerals, or quantum quirks, one thing's clear: the universe seems to have a subtle but undeniable preference for left-handedness. And that tiny imbalance might have been all it took to set the stage for life as we know it. Up next, we'll explore how even the bizarre rules of quantum physics might have had a hand in shaping life's earliest molecules, a frontier where science meets the truly unexpected. Now, let's venture into one of the most mind-bending frontiers of this cosmic mystery, where the rules of quantum physics might have nudged life into existence. At first glance, quantum mechanics and biology seem like strangers, operating on entirely different scales. But what if the bizarre behaviors of tiny particles, like electrons existing in multiple states, at once played a hidden role in shaping life's first organic molecules? Take photosynthesis, for instance. In modern plants, scientists have found evidence of quantum coherence, where energy from sunlight doesn't just hop randomly between molecules, but explores multiple pathways simultaneously, almost like it's taking every possible route at once to find the most efficient one. This quantum trick boosts the efficiency of energy transfer, and some researchers wonder, could similar quantum effects have been at work in the earliest, simplest molecules that preceded life? Here's where it gets speculative but fascinating. In the chaotic chemical soup of early Earth, certain molecules might have exploited quantum tunneling. This is when particles bypass energy barriers they shouldn't classically be able to cross, like ghosts walking through walls. For simple reactions, say, two molecules merging to form something new, quantum tunneling could have accelerated the process, making rare events happen just frequently enough to matter. Lab experiments have shown that tunneling can dramatically speed up reactions at cold temperatures, like those in space or icy planetary environments. Then there's the idea of quantum entanglement, where particles become linked across distances, instantly influencing each other. While this sounds like science fiction, some theorists suggest that entangled electrons in early molecular networks could have helped synchronize reactions, creating a rudimentary kind of communication between distant molecules. Imagine a proto-metabolism where parts of a system know what other parts are doing without any physical connection, a quantum whisper guiding chemistry toward complexity. Of course, there are big caveats. Quantum effects are fragile, easily disrupted by heat or noise, and early Earth wasn't exactly a quiet, controlled lab. Critics argue that in warm, wet environments, quantum coherence would collapse too quickly to matter. But supporters counter that certain niches, like the icy interiors of comets or shielded mineral pores, could have preserved these delicate states long enough to give life a subtle nudge. Whether quantum mechanics was a minor player or a hidden architect in life's origins, the mere possibility stretches our imagination. It hints that the universe's smallest quirks might have had outsized consequences, turning randomness into order and molecules into something alive. Next, we'll shift from the quantum realm to another icy battleground for life's beginnings, where frozen grains in space might have cooked up organic surprises. Now, let's turn our gaze to the frozen depths of space, where tiny ice grains drifting in the void might hold secrets to life's building blocks. Far from the warmth of stars, these frigid specks, laced with ammonia, methanol, and other simple compounds, could have been cosmic chemistry labs, quietly assembling organic molecules under the harsh glare of radiation. Picture this: a comet like 67P, the one visited by the Rosetta mission, is essentially a time capsule from the solar system's infancy. Its surface is a patchwork of ice and dust, bombarded by ultraviolet light and cosmic rays. When scientists analyzed data from Rosetta, they found something astonishing. The comet's icy grains contained complex organic compounds, including glycine, the simplest amino acid, and phosphorus, a key ingredient for life. How did these molecules form in such a hostile environment? The answer lies in the icy grains themselves. At temperatures close to absolute zero, molecules move sluggishly, but radiation provides the energy to kickstart reactions. When ultraviolet light or cosmic rays hit these grains, they break apart simple molecules like ammonia and methanol, creating reactive fragments. These fragments then recombine into more complex organics, almost like a puzzle assembling itself in slow motion. Lab experiments back this up when researchers simulate these conditions by irradiating icy mixtures. They consistently produce amino acids, sugars, and even nucleobases, the letters of the genetic code. One of the most intriguing aspects of this process is its efficiency. In the vacuum of space, without liquid water or moderate heat, traditional chemistry struggles. But ice grains offer a unique advantage. Their solid structure organizes molecules into tight arrangements, increasing the chances they'll interact. Meanwhile, the ice itself acts as a shield, protecting fragile organics from further radiation damage once they've formed. It's a delicate balance, just enough energy to drive reactions, but not so much that everything gets destroyed. The Rosetta mission also revealed another clue: the organic molecules weren't evenly distributed. They were concentrated in certain patches, suggesting that comet surfaces are dynamic factories, with some areas more chemically active than others. This fits with the idea that comets could have delivered a prebiotic toolkit to early Earth, a sprinkle of organic rich material that gave life a head start. Critics point out that while comets clearly carry organics, it's unclear whether these molecules could survive the violent impact of a comet strike. But recent studies show that some compounds, especially those sheltered deep within the comet's interior, might have a chance. And even if only a fraction made it intact over millions of years, that could have added up to a significant contribution. So next time you look up at a comet streaking across the sky, remember, it's not just a dazzling light show. It could be a remnant of the very processes that set the stage for life, carrying within its icy heart the faint echoes of chemistry that once might have sparked something extraordinary. Up next, we'll dive into a theory that swaps the icy void for the crushing depths of Earth's oceans, where supercritical carbon dioxide could have played an unexpected role in life's origins. Now, let's shift our focus from the icy reaches of space to the bubbling, high-pressure depths of Earth's early oceans, where an unlikely hero in the story of life's origins might have been hiding: supercritical carbon dioxide. Imagine a substance that's neither fully a gas nor a liquid, but something in between, a state where carbon dioxide becomes a powerful solvent under extreme pressure and heat. This is the strange world we're about to explore, and it could hold clues to how the first organic molecules assembled themselves. Near hydrothermal vents, where scorching water meets the cold ocean floor, conditions are just right for carbon dioxide to enter this supercritical phase. Here, under pressures hundreds of times greater than at the surface and temperatures soaring above 30 degrees Celsius, carbon dioxide transforms. It gains the ability to dissolve substances like a liquid while flowing through tiny cracks like a gas. This unique behavior makes it a fascinating candidate for prebiotic chemistry. In the lab, scientists have recreated these extreme conditions to test how supercritical carbon dioxide interacts with organic molecules. One striking discovery. It can help form nucleotides, the building blocks of RNA and DNA. For instance, when researchers exposed simple compounds like cyanamide and glyceraldehyde to supercritical carbon dioxide, they observed the spontaneous formation of ribonucleotides, key players in the genetic code. What's remarkable is that this process avoids some of the hurdles faced by other theories, like the need for concentrated ingredients or precise temperature control. The solvent properties of supercritical carbon dioxide naturally bring molecules together, boosting the chances they'll react. Another advantage is selectivity. Unlike water, which can break apart fragile organic molecules through hydrolysis, supercritical carbon dioxide tends to leave them intact once they've formed. This gentle touch might have been crucial for preserving early biomolecules long enough for them to accumulate and interact. Plus, the vents where this solvent thrives would have provided a steady supply of raw materials, carbon dioxide from Earth's mantle, mixed with minerals and gases spewing from the seafloor. Critics argue that while the chemistry works in controlled experiments, it's unclear how widespread supercritical carbon dioxide was on the early Earth. But proponents counter that hydrothermal systems were likely abundant, and even small pockets of this solvent could have acted as efficient microreactors, churning out organics that then vented into the surrounding water. There's also intriguing evidence from modern vents, where supercritical fluids are known to transport and concentrate metals, hinting at a similar role for organic molecules billions of years ago. So, while it might sound like science fiction, this theory suggests that life's origins could owe a debt to a form of carbon dioxide most of us never encounter. It's a reminder that the universe often finds ingenious solutions in the most unexpected places, whether in the frozen depths of space or the crushing, chemical-rich embrace of Earth's early oceans. Next, we'll journey to another world entirely, exploring the controversial idea that Mars, not Earth, might have been the true cradle of life's first molecules. Now, let's take a leap from Earth's ancient oceans to the rust-colored plains of Mars, a world that might have played a far bigger role in the story of life's origins than we once thought. Picture Mars as it was billions of years ago, a planet with lakes, rivers, and possibly even vast oceans, all under a thicker atmosphere. While today it's a frozen desert, back then, Mars could have been the perfect laboratory for brewing the first organic molecules, with conditions that sometimes outshined Earth's own. Scientists point to a few key advantages Mars had over early Earth. For one, its smaller size meant it cooled faster after formation, potentially offering stable, habitable environments earlier than our own planet. Mars also lacked the relentless tectonic activity that constantly reshaped Earth's surface, recycling its crust and possibly erasing evidence of early organic chemistry. On Mars, those ancient molecules might have had more time to accumulate and evolve undisturbed. Then there's the chemistry. Mars' soil is rich in minerals like boron and molybdenum, which are crucial for stabilizing ribose, a sugar essential for RNA, and aiding other prebiotic reactions. Studies suggest that the Martian surface, with its mix of clays and oxidizing compounds, could have provided a more effective workbench for assembling complex organics than many environments on early Earth. Add to this the planet's widespread volcanic activity, which would have supplied heat and chemical building blocks, and you've got a recipe for organic synthesis that's hard to ignore. But how would these molecules have made it to Earth? Enter meteorite exchanges. We know that rocks from Mars have landed on our planet. Over 30 Martian meteorites have been identified so far. These space travelers were blasted off Mars by asteroid impacts, drifting through space before crashing here. If Mars had already cooked up organic molecules or even primitive life, those rocks could have carried them to Earth, seeding our planet with the raw materials for life. The idea isn't as far-fetched as it sounds. experiments show that some microbes can survive the harsh conditions of space, and certain organic molecules are tough enough to endure the journey. Critics, of course, raise valid questions. Would organics or life really survive the violent impact that launched them from Mars, followed by millions of years in space and the fiery plunge through Earth's atmosphere? Some lab tests say yes. For instance, amino acids embedded in Martian-like minerals have been shown to withstand extreme heat and radiation. Others argue that even if Mars had a head start, Earth's more stable environment would have been better for nurturing life long-term. Yet the possibility remains tantalizing. Missions like NASA's Perseverance rover are now scouring Mars for clues, drilling into rocks that might contain traces of ancient organic chemistry. If they find evidence that molecules formed more easily there, or if future samples returned to Earth reveal structures akin to our own biomolecules, the Martian origins hypothesis could move from fringe to forefront. So, while Earth remains the most likely cradle of life, Mars might have been the kitchen where some of its key ingredients were first prepared, a reminder that the story of life could be more interstellar than we ever imagined. Next, we'll dive into another unconventional theory, where the humble molecule acetylene takes center stage in the cosmic drama of life's beginnings. Now, imagine a scenario where the building blocks of life aren't just floating in watery soups or clinging to comet ice, but forming in the fiery belly of a volcano. This brings us to one of the more underappreciated players in the origin of life drama, acetylene, a simple but mighty molecule made of just 2 carbon atoms and 2 hydrogen atoms. While it might not sound like much on its own, when acetylene gets together under the right conditions, it can spark a chain reaction that builds the complex chemistry life depends on. Here's how it works. Acetylene has been detected all over space in the atmospheres of gas giants like Jupiter, in the tails of comets, and even in the vast molecular clouds where stars are born. But what makes it special is its ability to polymerize, meaning its molecules can link up into long chains or ring-shaped structures called aromatic hydrocarbons. These are the same kinds of molecules we find in things like DNA and cell membranes. The key to unlocking this potential, extreme heat and the right catalysts, like the sulfur-rich gases billowing from volcanic vents. Lab experiments have shown that when acetylene is exposed to temperatures mimicking volcanic environments, think upwards of several hundred degrees Celsius, it transforms into more complex organics, including benzene, a fundamental aromatic hydrocarbon. What's wild is that this process doesn't need water or delicate chemical soups. It's a rugged, high-energy pathway that could have thrived on the hellish landscapes of early Earth or even other planets like Venus, where volcanic activity was and still is rampant. But why does this matter for life's origins? For one, these aromatic hydrocarbons are sturdy. Unlike some delicate prebiotic molecules that break down easily, they can survive harsh conditions, making them excellent candidates for enduring the chaotic early solar system. They're also versatile. Once formed, they can act as scaffolds for other reactions, attracting and organizing smaller molecules into more complex structures. Some scientists speculate that these could have been the backbone for early metabolic networks, providing stable surfaces where life's chemistry could take hold. Of course, this theory has its skeptics. Critics point out that while acetylene polymerization can create useful building blocks, it's unclear how these would transition into the kinds of molecules life actually uses, like amino acids or nucleotides. Plus, the high temperatures required might seem like a barrier. Could anything life-like emerge from such a furnace? Yet, recent studies suggest that in the presence of certain minerals, these reactions can occur at lower, more life-friendly temperatures, bridging the gap between fiery beginnings and biological complexity. What's fascinating is that this isn't just lab speculation. NASA Cassini mission found polycyclic aromatic hydrocarbons, the fancy cousins of benzene, raining down on Saturn's moon Titan, proving that these reactions do happen naturally in cosmic settings. If they can occur there, why not on a younger, more volatile Earth? So, while the acetylene pathway might not be the star of the show when it comes to life's origins, it's a compelling subplot, one that reminds us how many ways the universe has to assemble the puzzle pieces of life. Next, we'll explore an even simpler genetic precursor that might have paved the way for RNA, peptide nucleic acids or PNA, and the icy environments where they could have taken shape. Now, let's step into a world where the genetic code we know today might have started with something even simpler than RNA, a molecule called peptide nucleic acid or PNA. Picture this: before DNA and RNA became the star players in life's story, PNA could have been the quiet pioneer, laying the groundwork for genetics in a way that's both elegant and surprisingly sturdy. Unlike RNA, which is built around a sugar-phosphate backbone, PNA swaps that out for a backbone made of peptides, the same stuff proteins are made of. This small change gives PNA some unique superpowers, especially in the harsh conditions of early Earth. One of the biggest advantages of PNA is its toughness. RNA is notoriously fragile. It breaks down easily in water or under ultraviolet light, which makes you wonder how it could have survived long enough to kickstart life. But PNA, it's like the hardy cousin that doesn't mind roughing it. Its peptide backbone is resistant to degradation, meaning it could have stuck around long enough to catalyze reactions or even store genetic information. And here's the kicker: PNA can pair up with both DNA and RNA, suggesting it might have been a kind of molecular bridge between the first genetic systems and the ones life uses today. So where could PNA have formed? Two intriguing spots stand out: clay minerals and icy slush. Clays, with their layered structures and charged surfaces, are like molecular workbenches. Studies show that certain clays can help assemble PNA from simple precursors, acting as a sort of ancient 3D printer for genetic material. The clay's surface holds the molecules in place, encouraging them to link up into longer chains. It's a bit like stacking Lego bricks on a sticky table. Everything stays put long enough to build something meaningful. Then there's ice. Not just any ice, but what scientists call eutectic solutions, tiny pockets of liquid trapped in a frozen matrix. These icy microenvironments are weirdly dynamic. As the water freezes, impurities like salts or organic molecules get squeezed into concentrated droplets, creating hotspots for chemistry. In lab experiments, these icy conditions have been shown to stabilize PNA strands and even help them replicate. Imagine a snowball filled with genetic potential, sitting quietly until the right moment to thaw and unleash its secrets. But why hasn't PNA taken over the world if it's so great? Well, evolution is a game of trade-offs. While PNA is stable, it might lack some of the versatility that RNA eventually developed, like the ability to fold into complex shapes that can catalyze reactions. Still, the fact that PNA exists at all hints at a time when life's blueprint wasn't set in stone. It's a reminder that nature experiments, testing different molecular strategies until it finds what works. And here's something mind-bending. If PNA was life's first genetic material, it could mean that the line between proteins and nucleic acids was blurrier than we thought. Proteins handle tasks like catalysis. Nucleic acids handle information storage. PNA sits right in the middle, suggesting that these two pillars of life might have shared a common ancestor. So while PNA might not be in the spotlight today, its story adds a fascinating layer to the origins debate, one where simplicity and stability paved the way for complexity. Next, we'll look at another unsung hero in life's origin story: borate minerals, and how they might have solved one of the trickiest problems in prebiotic chemistry, getting ribose, the sugar in RNA, to stick around long enough to matter. Now, let's turn our attention to a tiny but mighty player in the origins of life: borate minerals. These unassuming compounds might hold the key to one of the most puzzling challenges in prebiotic chemistry: how ribose, the sugar backbone of RNA, managed to survive long enough to become part of life's earliest genetic code. Ribose is notoriously finicky. In the chaotic conditions of early Earth, this sugar tends to break down or react with other molecules before it can even get a foothold. But borate minerals like the ones found in ancient dry lake beds or hot springs could have acted as molecular bodyguards, shielding ribose from destruction. Here's how it works. Borate ions bond tightly with ribose, forming a stable complex that resists degradation. Think of it like a protective shell, keeping the sugar intact long enough to join forces with other molecules and build the first strands of RNA. The foremost reaction, a messy chemical process that generates sugars like ribose from simple precursors like formaldehyde, is where borate's magic really shines. Without borate, this reaction produces a jumble of sugars, most of which are useless for life. But when borate minerals are present, they selectively stabilize ribose, steering the reaction toward the one sugar that actually matters. It's like having a bouncer at a chaotic party who only lets the right guest through the door. Lab experiments back this up. Scientists have recreated prebiotic conditions with borate-rich solutions and watched as ribose levels spike compared to other sugars. Even more striking, borate's influence doesn't stop there. Once ribose is stabilized, borate minerals can also help it link up with phosphate and nucleobases, the other key components of RNA, essentially assembling the building blocks of genetics in one tidy package. But why does this matter? Because ribose's fragility has long been a stumbling block for the RNA world hypothesis. If ribose couldn't last long enough to form RNA, how did life even get started? Borate minerals offer an elegant solution, providing both the stability and selectivity needed to cross that hurdle. And here's the kicker: boron-rich environments weren't rare on early Earth. From volcanic steam vents to evaporating ponds, the stage was set for borate to work its chemical wizardry. Of course, this isn't the only theory out there. Some researchers argue that life might have started with other sugars or even sugar-free alternatives. But borate's role is hard to ignore. It's a reminder that sometimes the smallest details can tip the scales in nature's grand experiments. So next time you glance at a piece of borax soap or a borate-laden detergent, remember, these humble minerals might have been the unsung heroes that gave RNA and life itself a fighting chance. Up next, we'll dive into another cosmic puzzle: how hydrogen cyanide, a deadly poison today, could have been the unexpected spark that jump-started life's first molecules. Now, let's venture into the surprising role of one of the universe's deadliest poisons, hydrogen cyanide. Yes, the same compound that's toxic to life as we know it today might have been a crucial ingredient in cooking up life's earliest molecules. Hydrogen cyanide is everywhere in space. Comets, meteorites, even the frigid clouds between stars are packed with this simple yet reactive molecule. And here's the twist: under the right conditions, hydrogen cyanide can polymerize, meaning its molecules link together into longer chains, forming some of the key building blocks of life, like adenine, one of the 4 nucleobases in RNA and DNA. How does this transformation happen? Imagine hydrogen cyanide molecules floating in a primordial pond or trapped in icy cometary grains. When exposed to ultraviolet light from the young sun or mixed with alkaline water near hydrothermal vents, these molecules start linking up. Through a series of reactions, they eventually assemble into adenine, along with other useful compounds like amino acids. It's like a cosmic assembly line where a poison becomes a precursor for life's blueprint. Lab experiments have brought this theory to life. Scientists have recreated early Earth conditions by dissolving hydrogen cyanide in water and either shining UV light on it or adjusting the pH to mimic alkaline environments. The results: adenine forms reliably, sometimes alongside other nucleobases. Even more compelling, similar reactions happen in icy cosmic environments. When hydrogen cyanide ices are zapped with radiation simulating the conditions in space, they produce adenine and related molecules, suggesting this process isn't just an Earth-bound phenomenon. But why does this matter? Because hydrogen cyanide solves 2 big puzzles at once. First, it's abundant in space, meaning the raw materials for nucleobases were likely delivered to Earth via comets and meteorites. Second, its chemistry is versatile. Whether in a sunlit pond, a deep-sea vent, or a frozen comet, hydrogen cyanide can kickstart the journey toward life's molecular machinery. Of course, this isn't the only path to nucleobases. Other theories point to different starting materials or environments, but hydrogen cyanide's ubiquity and reactivity make it a standout candidate. It's a reminder that life's ingredients might have been forged in the most unlikely places, turning cosmic poison into biochemical gold. Up next, we'll descend into Earth's crust to explore a theory that flips the script entirely. What if life's first molecules didn't form on the surface at all, but miles underground, where heat, pressure, and minerals created a hidden crucible for chemistry? Now, let's dig deeper, literally, into one of the most unconventional theories about life's origins. Picture this: not on the stormy surface of early Earth, not near hydrothermal vents at the ocean floor, but miles beneath the ground, where intense heat and pressure create a hidden laboratory for chemistry. This is the world of deep crustal synthesis, where the very rocks themselves might have been the architects of life's first molecules. Down in Earth's crust, extreme conditions reign. Temperatures soar beyond the boiling point of water, and pressures crush molecules with forces unimaginable on the surface. But here's the fascinating part: these harsh environments could have been just right for cooking up organic compounds. When water seeps into the crust, it reacts with minerals like olivine and pyrite in a process called serpentinization. These reactions produce hydrogen gas and create alkaline fluids, both of which are key players in organic chemistry. In this subterranean world, carbon dioxide and other simple molecules dissolved in water can undergo transformations. Under high pressure and heat, they might form more complex organics like methane, formate, or even amino acids. Some experiments have shown that when water and carbon dioxide are subjected to crust-like conditions, think temperatures around 300 degrees Celsius and pressures hundreds of times higher than at the surface, they can generate organic molecules surprisingly efficiently. But how do these deep crust molecules make their way to the surface, where life could eventually use them? Enter Earth's natural plumbing system: geysers and hydrothermal vents. Fluids carrying these newly minted organics could be propelled upward through cracks and fissures, erupting into cooler environments like oceans or pools. Once there, they'd encounter milder conditions where these molecules could further interact, perhaps even assembling into the precursors of life. The beauty of this theory lies in its resilience. The deep crust is shielded from surface chaos: no asteroid impacts, no deadly UV radiation, just a stable, high-energy environment where chemistry can play out uninterrupted. It's a compelling alternative to surface-based theories, especially when we consider how harsh Earth's early surface might have been. Yet challenges remain. While lab experiments support the idea that deep crust reactions can produce organics, we're still piecing together how abundant these processes were and whether they could have generated enough material to matter. There's also the question of timing. If life started underground, how and when did it transition to the surface? Still, deep crustal synthesis offers a thrilling possibility that life's building blocks might have been forged in the planet's hidden depths, then delivered upward like gifts from the underworld. It's a reminder that the story of life's origins might be far stranger and more diverse than we ever imagined. And with that, we've reached our final stop on this journey through theories of life's molecular beginnings. Up next, we'll tie all these threads together, exploring how multiple pathways, space, vents, crust, and more might have combined to lay the foundation for life as we know it. Now let's step back and see the bigger picture. After exploring nearly 30 theories from cosmic chemistry to Earth's hidden depths, one thing becomes clear: the story of life's origins isn't a single path, but a tapestry woven from many threads. This brings us to the most inclusive idea of all: the hybrid multistage model. Instead of choosing between space, vents, or crustal synthesis, this theory suggests they all played a role, like pieces of a grand cosmic puzzle fitting together over time. Imagine the early solar system as a bustling construction site, with raw materials arriving from multiple suppliers. Comets and meteorites packed with organic molecules forged in interstellar clouds could have rained down on young Earth, delivering ingredients like amino acids and sugars. But these space-borne compounds needed a workshop to assemble into something more complex. Enter hydrothermal vents, where mineral-rich chimneys acted as natural laboratories, concentrating and organizing these molecules through heat and chemical gradients. Meanwhile, tidal pools and volcanic beaches might have provided the perfect settings for wet-dry cycles, allowing small organic chains to link into longer polymers under the sun's gentle nudging. Recent research highlights how these stages could interconnect. For example, studies show that meteoritic organics dissolve more efficiently in alkaline vent fluids, creating a bridge between space delivery and vent chemistry. Other experiments reveal that lipid membranes critical for cell formation self-assemble when space-derived organics mix with volcanic minerals in shallow waters. Even the deep crust gets a role, as geyser eruptions could have transported subsurface, made molecules to surface environments where they mingled with vent and space-sourced compounds. The strength of this hybrid approach lies in its flexibility. No single environment had to do all the work. Instead, each contributed what it did best. Space provided diversity, vents offered energy and organization, and surface pools enabled concentration and combination. It's like building a house where one team lays the foundation, another raises the walls, and a third adds the roof. Each stage essential, but none sufficient alone. Critics argue that hybrid models can feel like a catch-all, lacking the elegance of a single unifying theory. Yet interdisciplinary work is yielding surprising support. Astrobiologists now use computer models to simulate how organics might have hopscotched between environments, while geochemists trace isotopic signatures that hint at combined space and Earth origins for key biomolecules. Even the discovery of extremophiles microbes thriving in conditions mimicking early Earth's harshest niches suggests life could have exploited multiple pathways simultaneously. What's most exciting is how this mirrors nature's creativity. Life today thrives through collaboration, from coral reefs to gut microbiomes. Perhaps its beginnings were no different, a chorus of processes, each adding a note to the symphony. As we close this exploration, remember, the universe rarely chooses simplicity when complexity can tell a richer story. And in that complexity, we find not confusion, but a deeper wonder at how countless threads wove together to create the fabric of life. With that, we've reached the end of our journey through 30 theories, each a testament to science's tireless curiosity. But the search is far from over. New missions like Europa Clipper's dive into icy oceans or Mars sample returns may soon rewrite parts of this story. Until then, keep looking up and down and deep, because the next chapter in life's origin saga could be hiding anywhere. If you've enjoyed this cosmic detective work, don't forget to subscribe and hit the bell for more deep dives into the universe's greatest mysteries. As we wrap up this cosmic journey through the origins of life's building blocks, it's worth pausing to appreciate just how many ways the universe might have cooked up its first organic molecules. From the depths of hydrothermal vents to the icy reaches of interstellar space, nature seems to have experimented with every possible recipe. And here's the beautiful part: there's no reason to think only one of these theories is correct. Like a chef blending flavors from different cuisines, the universe likely combined multiple processes across time and space to create the ingredients for life. Picture this: a young Earth bombarded by carbon-rich meteorites, their payload of amino acids dissolving into warm tidal pools. Nearby, volcanic vents churn out minerals that act like tiny factories, stitching those molecules into more complex chains. Meanwhile, ultraviolet light dances on the surface of icy comets, sparking reactions that build sugars and nucleobases. It's not a competition between these scenarios, it's a collaboration. Just as a symphony needs strings, brass, and percussion, life's origins may have required chemistry from the heavens, the oceans, and the Earth's crust working in concert. This mosaic of possibilities isn't just scientific speculation. Missions like NASA Europa Clipper, set to explore the icy moons of Jupiter, could soon send back data showing how organics form in alien oceans. The Mars Sample Return mission might deliver rocks holding clues about whether the red planet's ancient lakes brewed molecules that later hitchhiked to Earth. Even here at home, labs are simulating the conditions of exoplanet atmospheres, testing how life's ingredients might arise under alien suns. Every discovery adds another piece to the puzzle, revealing a universe far more inventive than we ever imagined. So the next time you look up at the night sky, remember, the stars aren't just distant lights, they're part of the same story that led to you. The carbon in your cells, the nitrogen in your DNA, they were forged in cosmic furnaces, assembled in planetary cauldrons, and maybe even given a final polish in some primordial tide pool. We're not just inhabitants of the universe, we're its living, breathing archives, carrying echoes of events that happened billions of years ago. The search for life's beginnings is far from over. With every new telescope, every daring space probe, we're getting closer to understanding our molecular ancestry. Who knows, the next breakthrough might come from a lab in Zurich, a rover on Mars, or even a speck of dust from a passing comet. Until then, keep wondering, keep exploring, and stay curious. If you've enjoyed this dive into the cosmos' greatest mystery, don't forget to hit subscribe and ring the bell, because the universe still has plenty of secrets left to share. And with that, we've reached the end of our journey for now. But remember, science never stops asking questions. The next chapter in this story is being written as we speak, and you're invited to be part of it. Thanks for joining us, and as always, keep looking